Hello, everybody. I'm Tapo from University of Washington, and today I'm going to talk about our robot-assisted feeding system. This work was possible only due to close collaborations with multiple people in this picture. This is our group. And not too long ago, this robot Herb was actually at CMU. So robot assisted, like here is a video of our current robot assisted feeding system. Here you see the robot autonomously going, picking up a tool, which happens to be a fork in this case, and that uses multimodal sensing, like vision and tactile sensing in its fingertips to figure out what are the best control policies to pick up a certain food item, and what is the right amount of force to apply, and then figure out what is the best way once the food is picked up to feed someone so that it's easy for the person to take a bite. So now, like in the rest of the talk, I'll talk about how we achieved this. Now, why did we choose this application? Well, eating is an activity of daily living, right? According to a survey that was almost like 10 years back, there are around 12.3 million people in the US alone that needed assistance with ADLs. And like, imagine yourself asking someone else to feed yourself like every morsel of bite in your day-to-day life. It takes away like your feeling of control and independence. And robots have the potential to help with this by making them feel like they are in control of this. And so we thought, okay, let's develop a robot-assisted feeding system. But it's a very challenging task because it involves acquiring food items, which involves perceiving food in cluttered environments, manipulating them. You know, how do you pick up food items with widely different characteristics? Carrots are hard, celeries are hard, banana is slippery, watermelons may be soft. And then once you pick it up, how do you transfer this food item so that it's easy for the person to take a bite? So before we start developing this, we thought, okay, let's formalize this problem, right? And so, the idea is to be able to come up with a control policy that maximizes the success given a target and action. So, like, given the input is an image of a plate, and the target could be any one food item at one bite. And the action space are these actions of different ways to pick up a food item. And here we are considering only solid food items, plus some food items for like, how do you transfer this? And the way we came up with this action space was we actually studied humans, how humans do these tasks. And I'm not going to go into the details, but we developed a taxonomy, and based on this, we came up with this action space. So now, given this action space and this and the target, the goal is to select a policy that maximizes the success. And the way we implement this policy is we have, it's basically a mapping between image and haptics to control, like a delta position in the fork tines, right? So now, to actually implement this, this is how our framework looks like. On the left, you see, basically you will have an image of a plate with different food items. Now, using RetinaNet that was fine-tuned on these food items, it can generate bounding boxes. Now, this bounding box goes as an input to our network that we developed, which is called SPANet, or Skewering Position Action Net. And this outputs an action score map, which tells what is the best action to pick up a certain food item with the success probability, and where to skewer it. Now, we also found that in addition to picking up a certain food item that depends on the food item's characteristic itself, it also depends on its surrounding environments. So we also have an environment classifier that is input to this as a one-hot encoding vector. So this is our SPANet architecture, where the base is inspired from the AlexNet style base. And then after that, we have 3 fully convolution networks. And then we have this environment classifier that uses this information, puts this as a one-hot encoding vector before the final layer. And then the output is a vector, a 10 element vector, where 6 elements are for success rates for 6 actions that we got from taxonomy. And the 4 points are the 2 endpoints of the main axis. So this tells the robot where in the food item the robot should skewer. So here's a video. Here you see that the robot can pick up it's picking up these food items. And when the robot picks up these food items, it can not only pick up in the cluttered scenarios, but it also can pick up items that it has not seen. So the bounding box labels that you see, it only tells whether it's a food or not. It doesn't tell whether it's bell pepper versus it's strawberry or something like that. So this is well and good, but what if when it was generalizing to unseen food items, it was generalizing across some features? It can be shape or size. What if like we come across a food item that for which the robot doesn't even know what is the right action to pick up, right? And this can very well be possible because food is diverse. There's so many food items out there. And it's also difficult to use simulators because it's hard to model. Right? Like how do you go about modeling these complex food items? So we thought of leveraging online learning, where the idea here is that you observe the state, you choose an action, you get the reward, and you update your policy, right? Because then by exploring different actions while feeding someone or during real-time process, you can learn how to pick up certain items. And so for this particular byte acquisition part, we model this as a contextual bandit. Now, what is a contextual bandit? Like, I'm sure most of you are familiar with multi-arm bandits, right? Where you have an action, you take an action, you get a reward, but you do not really have a context. Now here you have a context where it can be an image. For example, here you see XT context, it can be images of different food items. And then we have a featureizer, which we use our SPANet network as a featureizer. And the policy, we take the last layer of this, and the policy uses this to map it to any one action. And these actions are these discrete actions that I talked about before from the taxonomy. And then we implement this action, and and in this case, for example, this banana, and the reward is only like it's binary, whether the food item is on the fork or not. That means whether the robot was able to successfully pick up the food or not. And then based on this reward, then we keep updating it, right? And the goal is to be able to minimize this cumulative regret, where you take the cost of all the actions that you took. You can see the equation below, from the start of the time point till the current time point, and then you minimize the regret with, by taking the difference with the best policy in class. Now, to actually achieve this, we use two algorithms. One is an epsilon greedy algorithm, where with epsilon probability you try to explore a new action, and the other is a linear upper confidence bound, LinUCB algorithm. And the idea here is that it looks for actions that have with the highest upper confidence bound. So it has more chances for exploration. So of course it sacrifices a little bit of learning speed, but with for improved regret. So this is how our final set work looks like, where you have detection, you have the network, this is the policy, and then you sample an action, you take the reward, and this goes on and on, right? Now, here, so for example, you'll see how it works. To start, red is the correct action. But to start with, the robot had very low confidence in it, right? But after exploring multiple times, it figured out what is the right way to pick up this slippery banana, and then the confidence increases and it converges to the correct action. Now, while doing that, it does not forget how to pick up like the other items, and also next time a banana is given, it remembers what action was taken. So even if one banana was sacrificed, you could, from the next banana, you know how to pick up different items. Now, to evaluate this, we actually brought in people with spinal cord injuries for different levels of like mobility limitations, and the robot fed them different food items, as you can see in this. I'm not going to go into the details of this study, but people were generally highly accepting of this, as you can see from one of the comments, which says the technology allows me to do more things on my own, of course giving me more independence, making me feel more free, and gives me something to look forward to. So basically the key takeaways here is that assistive feeding is a high impact and at the same time technically challenging task, and robots have the potential to help with these tasks. However, though we have some promising directions, there are lots of future work to be done, because the feeding technology has many complex social, cultural, and self-identity implications that goes beyond just the functional requirement of picking up a food and feeding someone. And this is what we are looking into. Here are some open data sets for you to play around, and I'm happy to take more questions. Thank you.